Hello everyone. So this is a mathematical physics problem which is quite interesting because it includes the solving of or the finding of the general solution of an ordinary differential equation. So this is actually an RLC series circuit with AC driving voltage, or the resistor, inductor, capacitor series circuit. And the circuit is given by this figure. And as we know, by applying the Kirchhoff's voltage law, we have this general form of the ordinary differential equation that is derived from this circuit, and it's given by this equation. So the problem is to find the general solution for this problem. This is actually quite long because in problems like this, it includes the finding of the homogeneous solution of our ODE and the particular solution. So anyway, let's start to solve this problem. So we first copy this equation right here that was derived by application of the Kirchhoff's voltage law. And then the next step, or the first step that we shall do to solve the general solution here, is actually to differentiate this equation with respect to t, so that this equation will become L times d squared of I with respect to t. We have R times di over dt, and then we have 1 over c. We have times dq over dt. Okay, so we do this because we want to arrive at a linear second order ordinary differential equation and apply the techniques that we know in solving such equations. So anyway, so the right hand side of the equal would be equal to cosine of, let me just copy this, cosine of omega t times the derivative of omega t, which is simply omega. Now, so we have this equation for this. But we have to take note, we can actually reduce this equation or rewrite this equation such that we have dq over dt is actually I. The current is just the rate of change in, or just the moving charges, so that our equation right here, this one, would be equal to, this is now 1 over c instead of 1 over c dq over dt. This becomes I over c. And we can notice that our equation is actually, this is actually similar to the mechanical oscillator equation or mechanical harmonic oscillator model, where our inductance L is similar to the mass. We have the resistance is the damping B. We have 1 over c is our spring constant, and so on. But anyway, to solve the general solution, of this linear second order ordinary differential equation, we have I as a function of t is equal to the sum. This is actually the sum of the homogeneous solution and the particular solution. So, which means that for us to be able to find the complete general solution, we have to solve first for the homogeneous solution and the particular solution. So I think it's better if we structurize our solution by dividing it into two. We have the first one is by by finding the homogeneous solution, and the second one is by finding the particular solution. So we have finding first the homogeneous solution, and then the next one is finding the particular solution. Okay, particular solution, that's IP, of course, as a function of t, And for the homogeneous solution, that's IH as a function of t. So we start with letter A for this, because this will be the second part of our solution. So we first start with letter A. Now, likewise, we also structurize our solution in letter A. So we have this step by step. I call it step by step, and I find it more feasible and more practical to have a step by step derivation, so that we will not be lost, right? So we start with, let me first edit this. How do I wait? So we start with, and the first step is to find the characteristic equation. And if you recall, in solving a homogeneous, or in finding the homogeneous solution of a second order ordinary differential equation, there are many techniques that we can use. One is by substitution of an exponential ansatz, and the second is through Frobenius method, among others. So it's actually up to you which is more comfortable to use. Is it substitution of an exponential ansatz or the Frobenius method? But for purposes of this discussion, I decided to just use the exponential ansatz. So this is as a function of t. That is, we propose that the solution to this problem is actually exponential. That is, it is equal to e to the pt. And then substitute e to our original equation. Now we have to take notes. What is our original equation for this? So this becomes so that our homogeneous equation will be equal to this one. We just have to copy it again, and since it's homogeneous, we equate this to 0, right? Which means that we have to look for the second derivative of our IH with respect to t, and the first derivative of IH with respect to t. No problem with IH, because we already have provided this. That is, IH is equal to e to the pt. But anyway, this is quite straightforward. So we have L. What is the second derivative of our IH with respect to t? So that's simply p squared e to the pt, right? And then for the first derivative, we have p times e to the pt. We have this is 1 over c times e to the pt. Okay, perfect. So we have this one. Let me just e to the pt. Yes, and of course this is equal to 0. And we can notice that we have a common term for this equation. We have e to the pt is common. Let me just write this properly. Okay, which means that we can divide both sides by 1 over e to the pt. So we have 1 over, this is e to the pt, 1 over e to the pt, so that we can cancel out e to the pt's. We have, let me just cancel this out for clarity. We have e to the pt. We also cancel this, so that what's left is actually a quadratic equation, which means that by application, by using the quadratic formula, we can find the roots and find the general solution out of the roots that we can solve. So we are left with the quadratic equation L p squared plus rp plus 1 over c. 1 over c is equal to, this is 1 over c is equal to 0. Or we can actually rewrite this into p squared plus r over l times p plus 1 over a CL, or simply LC, it doesn't matter, and this is equal to 0. And as I've said, this is a quadratic formula, a quadratic equation where A is equal to 1, we have B is equal to R over L, and then C is equal to 1 over LC. And then find the roots, right? So we have to solve this. The next step is actually to solve the quadratic equation. A quadratic equation. We have quadratic equation. Okay, and to do that, we use the quadratic formula. So we have P12 equals, okay, we have negative B plus minus square roots of B squared minus 4AC. We have 4AC over 2A. And this is very straightforward. We just have to substitute the given values for A, B, and C, so that P12 equals negative R over, what is this? We have negative R over 2L. Anyway, this is quite straightforward, right? Plus minus, we have 1 over 2L, 1 over 2L times what? Times the square root of R squared. We have R squared minus 4L over C. Yes. So we have here the two roots, which means that we have P1. Let me just copy this. We have P1 equals the plus. It's up to you. It's also possible that this is your P2. You have P2 is equal to, this is the minus 1. This is the minus 1. But we can notice that there are, of course, there are two roots, but we can notice that the two roots, both of them, are real numbers. None of this is imaginary. And since these are all real roots, we know the general solution for this. That is, if you can recall, the general solution for such is IH, as a function of t, equals C1 e to the pt. We have two roots, so that's P1t plus C2 e to the P2t. So that's P2 times, that's P2 times t. And we just have to plug in this P1 and P2 so that we have IH as a function of t equals C1 exp. Maybe I will put this inside the bracket. So we have P1, this is our P1, times t, right, plus C2 exp. Okay, we have the P2t, so we just have to copy P2 times t. So this is now our equation for this is now our homogeneous solution, the first part of our solution. Let me just, okay. So this is now our homogeneous solution. Let me just highlight this so that it's easy to come back and look for this if it's inside the box. So this is now our homogeneous solution. But the good thing about mathematical physics, the good thing about physics is that we don't just end our solution into the final equation. And what's interesting in it is that we also interpret the results, the final equation that we get. And that's actually what separates physics and mathematics sometimes, because in physics we try to explain the physical interpretation or the physical meaning of our final equation. But anyway, we can notice that in this equation, the negative real part. Of course, these are all real integers. The roots are all real. So we have negative real part. We have negative r over 2l. That's less than 0. Of course, now since this our resistance and inductance are greater than 0, this ensures we have exponential decay. What do we mean by exponential decay? That is, as our time, we have as time approaches to infinity. We have approaches to, where is the infinity in this case? Anyway, no problem. We just have to write it down here manually. So as t approaches to infinity, we can notice that our homogeneous solution approaches to 0. So we have IH approaches to 0, and we call this as transient currents. So anyway, this is, as I've said, this is the homogeneous solution of our problem of our RLC series circuits with a voltage V0 sine of omega t. And as I've said, this is just the first part of our solution. Remember that we divided the parts or the solution into two. We have the first part is for the calculation of the homogeneous solution, and the second part is for the particular solution. So we are now done with the first part. All that is left to do is to solve for the second part, and that is for finding the particular solution. And this is quite tricky as compared to the homogeneous solution, and I prefer to discuss this in our next video. So please stay tuned for the next video as we will be solving the particular solution. Thank you very much for listening and watching this video.